So the agenda for today's presentation is going to talk about, basically going to help answer all of these questions for you. What is bursty traffic? What do we mean by that? Why is burst testing important for you? Where should you test for burst problems in your network? What are some of the causes of burst problems? And what is the best methodology to test burst? And along with that, we will share some live demonstrations of our burst testing solutions with you. And of course, have time at the end for questions and answers. So first, I want to start off by explaining what do we mean by bursty traffic. If you look at the highest layer of the OSI networking model, layer 7, that's the application layer, which applications are we talking about that are going to be bursty? So those are going to be your data applications, your internet traffic, file transfers, FTP, email, SharePoint or Communicator, uploading a photo to Facebook, for example, or downloading a video from YouTube. All of these applications are going to produce bursty traffic, and they're all transported over the network using TCP in the transport layer 4. Now, TCP by nature is going to produce bursty traffic at layers below it, at layers 3 and 2 in the network. So if you were to look or graph at your throughput over time, it's going to be quite variable, and it's going to have these spikes or peaks and valleys. And it's really going to have bursts in very short periods of time. And so that's what we mean by bursty traffic. On the flip side, we have constant traffic. So those are where our real-time services come into play, voice and video. Voice and video are transported in layer 4, the transport layer, using UDP. And this is going to produce a constant bit rate over time. So if you were to look at that at layers 2 or 3 at your network, it's going to produce the same constant bit rate of traffic over time, and you won't experience the same kind of bursts that you do with data applications. So I want to take a moment to look at the market situation as we've seen it, and working with wireless providers, I'll start with, and then we'll talk about wireline providers. But what we're seeing is that as wireless providers transition from T1 and E1 links to Ethernet, they're seeing that bursty data applications running on all of our smartphones are causing, in many cases, frame or packet loss at either the demarc point to the backhaul network or at some bottleneck point within the wireless network or the backhaul network. So one of the benefits, as we transition to LTE, is that it gives you higher bandwidth, which is what we need. But what are the applications that people are running on their smartphones that need this higher bandwidth? It's all of those data applications that I was just talking about. So people are running more and more data applications at higher bandwidth over the wireless network and then therefore through the backhaul network. This higher bandwidth usage is resulting in more and more bursts on your network in shorter time periods. And this makes the problem even worse and more noticeable at higher bandwidth. And so looking at a concept of TCP, we have retransmissions. So because TCP uses retransmissions to guarantee error-free transport end-to-end of our data applications, whenever a burst of traffic causes frame loss in the network somewhere, retransmissions are going to occur. These retransmissions will then slow down the performance of those data applications running on our smartphones. So because bursty traffic is causing these frame loss or packet loss that we see, it's degrading the service performance for individual users, and not only these individual users, but can do so for multiple users because they're sharing the same medium in many cases. So bursts by one user can sometimes cause loss for another user. And another key point that wireless providers are taking into concern is that their bandwidth and their wireless spectrum are a very valuable asset for them. And they don't want to be wasting any of that bandwidth or that spectrum having to do a lot of retransmissions because of frame or packet loss. So because of this, because we're seeing this problem arise more and more, there's been a shift in the service activation test market in that wireless providers are starting to add committed burst size, or CBS, to their service level agreements, or their SLAs. And they're conducting an end-to-end burst test to help identify these potential bottlenecks and to identify any frame or packet loss that's occurring. So in this example, an end-to-end burst test, CBS test, can be conducted using between an Ethernet probe like the QT600, for example, or a handheld portable such as the T-Bird or MTS5800 to run an end-to-end burst test to look for frame or packet loss. And by end-to-end, I mean from the cell site to the switching office or vice versa in terms of direction. So now taking a look at the situation that wireline providers are facing. So because the wireline providers are offering Ethernet mobile backhaul services, they're running into many of the same problems that I just previously outlined with the wireless folks. These bursty mobile data traffic applications are in many cases causing frame loss, either at the demarc device or at a bottleneck point somewhere through the backhaul network. Now, looking at it from another perspective for wireline providers, it can also have the same kind of problems with your Ethernet business services. So I'm talking about services that are offered to customers such as financial institutions, banks, or hospitals, etc. And we've seen many instances in this case where end customers complain of poor throughput and blame the provider network. And this poor throughput in many cases can be a result of frame or packet loss on their bursty data applications. Additionally, bursty data traffic can impact higher priority services in class of service or triple play offerings. So we've seen this in several instances where bursty data traffic can cause loss on your real-time services, voice and video traffic as well. So therefore, the resolution for wireline providers has also been to conduct these end-to-end burst tests from demarc point to demarc point, either between two customer locations or in the case of a mobile backhaul from the cell site to the mobile switching office, and adding a CBS parameter to their service level agreements as well, and conducting an end-to-end burst test. In this case, you can do it between, again, an Ethernet probe and a portable or between two portable instruments. So I want to take a moment to talk to you about what are the end user pain points. So the end user being either your wireless customer or your Ethernet business customer. If there's a lot of frame or packet loss of bursty data traffic, they're going to experience this in a negative way on several different data applications. For instance, it is going to take a really long time to download a web page, whether it's on their PC or on their smartphone. Or it could take forever, seemingly, to upload or download a file. Or when they're trying to download and view a video, the video application is very slow in trying to do that. Or it takes a long time to retrieve their emails, for example. Or just common complaints of the network appears sluggish or slow. And bursty frame loss can also result in poor throughput results by an end customer if they're trying to run their own iPerf throughput test, for example, between two laptops. And iPerf is using TCP bursty traffic. And if the network can't handle bursty traffic appropriately, they will see poor throughput results and all of these other kind of negative problems I just described. So now I want to talk about what causes network buffering problems, burst problems. So network buffering is the key point that I want to bring up here when we're talking about looking for burst problems. It's when there is a downshift in the network that a buffer comes into play. So a network buffer, or queue, is an important part of any network device. And what this is showing, this picture here, is a higher speed business customer LAN, for example, at a 1 gigabit Ethernet rate that is then connecting into the provider WAN which is 100 megabits per second service. So it's connecting at this DMARC device, an edge switch, for example, that this downshift is occurring from the business customer LAN to 100 meg WAN service that they're buying, this downshift. So when this downshift occurs, these switch buffers help to smooth that transition so that no traffic is dropped. Now, there's only so much that these buffers can do, and there is a limit. So the greater the downshift in speed, the more likely this buffer is to overflow and then, of course, drop frames or packets. So this is a very important part of when we're testing burst, is through a downshift point in the network. So looking at points of concern here, it's usually at the edge or access switch DMARC part of the network, or it's at an aggregation point in the network. So the aggregation point could be within your backhaul metro core, if you will, where you're aggregating several gig-E links into a 10 gig pipe, for example. So it's those 2 points in which this downshift in speed occurs in your network and where there is a likely buffer size problem, that's a buffer that's not large enough to be able to handle the bursty traffic. Now, looking in the core of the network here, if that's really not a point of concern for bursty traffic, because if you're connecting 10 gig to 10 gig, for example, there's no downshift in speed, and so that wouldn't be a likely point of a burst problem. So keep that in mind. So this animation here is showing you an emulation of 3 different types of services, emulating a triple play application, for example, voice, video, and data traffic. And it's sending these 3 different types of traffic at a 1 gig LAN interface speed. So emulating the kind of traffic that a business customer is generating into your network, and then coming out the other end on the provider network at 100 meg interface speed. So we've done a lot of field testing and a lot of lab testing, looking at the capabilities of various equipment and these buffer sizes and configurations. And when you generate this traffic at a 1 gig going into 100 meg WAN, and you're using all constant bitrate traffic, this buffer has no problems and is able to handle the constant rate traffic without any drops. And it's not until you actually emulate that data traffic as real bursty traffic, like we'll see in this next animation slide, that you actually start to stress the network buffer and see that frames are being dropped or lost. So this is a better way to emulate your data traffic by sending bursty traffic, because that's what these data apps are really going to be doing on the network. And you can see that not changing anything in this scenario other than sending bursty data traffic through, the buffer now is stressed and is starting to drop packets or frames. And we've seen in some cases also that if the prioritization or queuing hasn't been set up properly, the data bursts can cause voice and video to start dropping as well. So I want to share with you a real case study that we participated in with a Ethernet backhaul provider in North America. So this backhaul provider was running their regular SLA verification tests before handing the service over to the wireless customer. And this wireless customer included a new SLA parameter for CBS. It was a 64 kbyte CBS. So the service was a layer 2, 100 megabits per second CIR, committed throughput, with the ability to burst 64 kbytes above the CIR. And this provider needed to be able to prove compliance to that. So they tried to do so by using the back-to-back test found in the RFC 2544. And they ran into several problems. First, it was taking hours to actually run this back-to-back test as it was specified by the RFC 2544 several years ago. And secondly, the test was failing, and they were unable to burst 64 kbytes without losing packets or dropping any frames. So we helped them run a CBS test from end to end, a new CBS test that we're going to show you as part of our RFC 2544. And running this test now can take less than 5 minutes, and it was able to expose a default buffer size that was too small at the switch that was aggregating several 1 gigs worth of cell site traffic back to a 10 gig pipe into their core. This default buffer size was only set to 20 kilobytes. So you can imagine if the buffer is only 20 kilobytes in size, it's unable to handle a burst of 64 kilobytes worth of traffic. So buffer size settings are configurable and can be changed. So they increased the buffer size and to a large enough amount, and then it was able to handle the 64 kbyte burst of traffic without dropping anything. So now I want to hand it over to Barry, who's going to discuss how to test burst, some more technical details behind burst, buffers, and policers, and do some live demonstrations for you.
Okay, thanks, Rachel. And hello, everyone. So in the technical section, we're going to cover the fundamentals of network buffering and policing. We'll have demos of CBS testing and TrueSpeed, and then we're going to go ahead and wrap it up with a discussion of best practices. So first, it's really important to understand the difference between network buffering and policing. Network buffering and queuing occurs when a network device is overutilized. This oversubscription can happen in devices that implement QoS and those that do not. So the way the device handles the oversubscription will vary whether a QoS policy is in place. This webinar is going to focus on the predominant occurrence of network buffer issues, and this is generally an egress problem. Okay, and that occurs when the ingress rate is greater than the WAN egress rate, and that's something that Rachel mentioned in her slide. So in the diagram on the right, we see here that an end customer access link is a gig, and it's downshifted to a WAN port speed of 100 megabits per second at the egress. The bursts that Rachel illustrated in the previous slides are going to occur at the gig rate, and the egress buffer of the network device has to be large enough or packets are going to get dropped, and bad things happen to customer TCP application performance when that happens, especially over a WAN. So now, I'm going to bring up this topic here of policing. Now notice the policing function occurs at the ingress side. That's a key takeaway point of a device. And that corresponds to a provider who's going to rate limit to the contracted SLA. SLAs have traditionally been guaranteed just the committed information rate, or the CIR, but a growing trend is that the SLA also guarantees a committed burst size, or the CBS. So a buffer size is specified in bytes, and CBS is specified in bytes as well. But there's a key difference here, and this is something that generally causes confusion. The difference is a buffer is a true memory, while CBS is not really memory, it's a metering function. It's an accounting system. So in other words, CBS at the ingress is simply measured by the number of bytes within the policer time period. Okay? So in the policing example, the access and WAN links are both at a gig, but the policer is set to 100 megabits per second. So we're actually going to demonstrate this very situation in a little later in the webinar, but the key takeaway point is that a buffering occurs at the egress side of the network device, as a general rule, while policing is an ingress function. So next slide, let's go ahead and dive in a little bit more into policing. So simply stated, CBS is the number of bytes that an end customer's traffic can burst above the CIR. The question then becomes over what time interval, because you could burst traffic and you have to have an interval for which that's measured. So the formula for this time interval is actually pretty straightforward, as you can see below. First, we take the CBS in bytes, and then we multiply it by 8 to get bits. So in this example, we're going to take the 100 megabits per second times 8, the 64 kbyte CBS times 8, divide that by the CIR, and the result's going to be time. So in this example, we get 5.12 milliseconds. So a lot of words there, but really all you have to remember is that the subscriber traffic can burst 64,000 bytes within a 5.12 millisecond period on top of the 100 megabits per second CIR. So another thing I want to add, probably many of you have heard of this, it's the policing function is commonly implemented using the so-called leaky bucket algorithm. And this dates back to the frame relay days. I'm only going to discuss the CIR-CBS portion of the bucket. And in the diagram, you can see what represents the CBS bytes, and the bucket can fill with CIR plus CBS. So it's filling with bytes, and it's also draining at a CIR, and the burst can happen, but if the bucket overflows, then generally a provider will drop the traffic, but you can also mark it, and it can go into the other bucket of EIR and EBS, but that's outside the scope of this webinar. And finally, the MEF provides all the details of all these parameters in the leaky bucket algorithm in recommendation 10.2. Okay, so on to the next slide. So this is an illustration of bursty traffic, and it's a simple illustration of how TCP traffic bursts within a policer timeline. As long as each of the green bursts of TCP frames don't exceed the CBS, or the number of burst bytes, within the policer interval, then the packets won't be dropped. So here you see this is representative of bursty TCP traffic bursting, so it's allowed to do that every burst interval. Okay, that's really all this is trying to show. But in the remainder of this webinar, we're going to discuss a best practice approach to testing CBS, or buffer size, and additionally, how to take this one step further and truly verify the performance of end customer traffic using JDSU's TrueSpeed technology, which is based on RFC 6349. Okay, so now let's discuss the topic of testing CBS and buffer sizes. Whether the goal is to test the CBS of a policer or the buffer size in the network, a layer 2-3 test is always the first step. JDSU offers a CBS test option with our enhanced RFC 2544 and our 1564 offering. Those of you that want to run RFC 2544 as part of the normal installation process, you might be familiar with the back-to-back test, and that test sends a burst of bytes, burst of frames back-to-back into the network. The JDSU solution provides the option to conduct a normal back-to-back test, That would be the checkbox shown unchecked here, or a CBS test. And it's a very simple addition to the standard RFC test. As you can see in this diagram, the CBS option is selected, and along with that, the CBS is specified in kbytes. And here we have an example of 64 kbytes. The test is executed, and the results are provided in a very simple green, red light kind of thing. You get the pass, and I have some things highlighted here that show you the burst size that was achieved, and mainly you want to make sure that for whatever frame size you tested, you have 0 lost frames. Okay, so now we're going to go into the demo of this exact same scenario. Now your WebEx is going to flip around just a little bit because I'm actually going to share, well, actually I want to show you the demo configuration first. Sorry about that. So in the demo, there are 2 JDSU T-Bird 6000s you see in the diagram, and they're communicating through a Cisco MEF standard switch. The Cisco Policer is configured for 100 megabits per second and a CBS of 64 kbytes. Okay, so what you have here is the near end T-Bird going to a Policer and talking to the far end T-Bird. Notice that the round trip time is going to be 10 milliseconds, and that's actually in a lab using a network impairment device. Now in the test, we're going to loop back the far end T-Bird, but you could do bidirectional concurrent testing as well. So now we're going to go on to the demo, and let me go ahead and I have to just change what I'm sharing here. Hold on just 1 second. And we'll go ahead and do the CBS test. Okay, so now what you see, some of you may have not used our 2544 implementation, but the configuration is of the 2544. You have options to pick for all the tests. In this case, we're going to keep the demo consistent with the time frame we have. We're going to run the throughput test and the back-to-back or the CBS burst test. Now, you have many different frame sizes you could choose. In this test, we're going to run a smaller frame size of 128 bytes, and then we're going to run a larger frame size of 15, 18 bytes. Notice that we're going to set the maximum bandwidth or the CIR to 100 meg. Let's go to the back-to-back tab. Similar to the slide before, we're selecting the committed burst size of the test versus the standard RFC, and we're going to go ahead and send 64 kbyte test, and it's as simple as that. We're just going to go ahead and click the run button. So you see a message that pops up. The near end T-Bird is just giving us the status that it's going ahead and looping up the far end T-Bird. I just want to mention again that you can do CBS testing in loopback manner. It's more probably accurate to do it in each direction, although that may not always be practical. Let's see, right now it's just giving you some status. It's showing it's working on the 128 byte throughput test. So this is going to test it at the 100 megabit per second CIR. And then after that's done, it'll move on to the larger frame size, which is 1518 bytes. Okay, let's wait for that test to complete, and I'll show you a nice summary view. Okay, so we're going to finish that. It's moving into 1518 bytes. And now let's look at this a little bit. I know this is a little bit of information, but what this is saying is the 128 byte test passed the CIR test. Now you can see we have a color coding here giving the layer 1 through layer 4 throughput, because what happens is, with a small frame size, you have a lot of overhead. The overhead is more significant of the Ethernet header. So it's going to get, as you look at it from layer 1 through layer 4, it's going to be less throughput at that layer 4. But if you move into the 1518 bytes that we just concluded, which also passed, you're seeing the same color scheme on the throughput, but you're seeing a much smaller difference, and that's because out of 1,518 bytes, the Ethernet header is a much smaller portion of that, so the overhead is smaller. Now, go back to the progress. It's running the 128 byte frames on the CBS test, and the first test passed. Actually, both tests passed. It's coming up with a screen that's telling us that we can generate a report. of everything that we just did, so we're not going to do that today. But again, we're going to look at the results of the CBS. We see that the 128 byte test passed a 64 kbyte burst. The 1518 passed, and we have 0 frame loss. So that concludes this part of the demo. And before I move back to the presentation, Rachel, would you like to add anything else about the demo?
Yeah, just that. So what you've seen here is a very quick, demo of the throughput test as part of the RFC 2544 implementation and the new CBS or burst test as well in the same automated script. So, and if you were doing a service verification, whether for an Ethernet business customer or a mobile backhaul, or if you were a wireless customer, your end-to-end verifying the end-to-end service that you're getting, this is, the recommended test that you would want to run, including, I would say, your delay and packet jitter delay variation and frame loss measurements, which we didn't demo, but are as part of this test. So that is, kind of step 1 minimum of what we recommend you would measure for this Ethernet service verification. So the throughput, 100 megabits per second, that passed, and the CBS test passed as well in this case. You could burst 64 kbytes without dropping any frames.
Okay, so I'm going to go ahead and go back to the slides for just a minute, and then we're going to do another demo, so hold on one more time here. And we'll go back to the slide deck. Okay, so that was the end of that demo. But now what we want to talk about here is a situation that providers understand all too well. So obviously a CBS test is a better way to install a service versus traditional CIR-based testing, since CBS attempts to emulate bursty traffic but only to a certain degree. The bottom line is this, though. End customers' business applications are TCP-based, and even though the provider does not offer a TCP SLA per se, we found that it's highly beneficial to run TCP-based installation tests based off of RFC 6349. And since the JDSU implementation of RFC 6349 TrueSpeed has been enhanced and automated significantly, it truly can be the same truck roll, same technician that can run the TCP test in under 5 minutes. So the end goal that we all know is to install a service and have no disconnects between the provider and the end customer expectation. So I know this sounds like nirvana, but we've seen that providers who adopt TrueSpeed into their service installation, they're seeing a lot less truck rolls and churn with their end customers, because you're both now talking the same language. The throughput test that's being conducted by the end customer and the provider are very similar, if not the same. Better yet, they're standardized. So let's go into another demo. I want to show you what we're going to do next. So in the previous demo, 2 JDSU T-Bird 6000s were communicating through Cisco MEF standard switch. And again, the policers configured for CIR of 100 meg, so really nothing's changed here as far as the configuration. It's identical, but instead of running just the RFC 2544 with CBS option, this time we're going to run live TCP traffic. Okay, we're going to run 2 sessions, each with a 64 kbyte TCP window. So just think of that, it's almost identical to 2 users at a customer prem simultaneously doing an FTP from the near end T-Bird to the far end T-Bird. Okay, so we're going to go on to the demo, and again, your screen will flip one more time. Okay, we're going to go look at the user interface of the near end T-Bird. Okay, sorry about that. Okay, so when we look at the near end T-Bird, it's a very simple setup. You just tell it what TCP port to connect to, and then what the CIR is. So similar, just exactly the same type of terminology as what you're all used to in Ethernet. Turn up. We have a round trip test that we want to run, and we want to run the TCP throughput test. The configuration that I'm configuring can be saved, but right now I'm just going to show you the manual steps. The duration of the round trip test will be 10 seconds. And remember that I said we're going to generate 2 FTP-like streams or sessions from the near end to the far end of a 64 KB window. And there's the 2 connections. As I mentioned earlier, you can save the config, but due to the time constraints we have here, we're just going to go ahead and run it. So that's it. That's all you have to do to run a TCP test. It's going to run what we call a round trip test and the TCP throughput test. And again, these are the tests defined in RFC 6349. There's some other tests that the full-up implementation of TrueSpeed can run. But again, we're just trying to demonstrate the concepts of burst today. And the way that the product is working is that the hatch is running, the red or green means pass or fail. So the round trip was completed. We see that we're getting a graph here of the 10-second run of the round trip, and the round trip was 10 milliseconds approximately, as we indicated in the demo slide. Now it's actually running a TCP throughput test. Now in this test, the near end T-bird is generating 2 sessions to the far end T-bird, 64 KB window. So that's really not a lot. That's really just 2 users that would be doing an FTP from the near end to the far end. And so the test should take just a little bit longer to run. We'll get a pass-fail verdict here. So I guess the key point is that we saw that 100 meg layer 2 test with CBS of 64 KB would pass. Here we see TCP throughput though did not pass. And if you look at this, how much different it can be with loss on a WAN, we see that the actual layer 4 was 61 megabit per second approximately, and the ideal layer 4 was 95. So you can imagine the churn that causes. When a customer tries to run a simple FTP after the service is installed. Here for the more advanced user, we have graphs that show the throughput and the retransmissions, and also the throughput versus round trip. So the red on the y-axis, the policer causes a lot of retransmissions. So I'm going to have to go back to the demo. We're running just a little bit tight on time here, because I know we want to make sure we have 15 minutes for questions and answers. So I'm going to stop the share on the demo, and this will be the last time your screens will flip around. We're going to stick to the slides here for the remainder. Okay, so the demo, I just want to do a recap. The main point is the CBS test passed, as you can see here, and the TrueSpeed test failed. That's really what we want to do. So in other words, the CBS was configured properly for what you intended it to be configured, a 64,000 byte, but that didn't necessarily mean that end customer traffic is going to run properly. So in the first demo, again, we configured the 2544 CBS option, 64 KB, you can see there, and that all passed. But when we ran the TrueSpeed test traffic per RFC 6349, it was quite different. And there was at least, this is a screenshot, but we saw 60 today in live. This is always going to vary a little bit because of the way TCP operates. And again, you can only imagine the finger pointing, and I'm sure if you're on this webinar, you've experienced that finger pointing. So I just want to, the next question becomes, well, like, why does TCP behave that way? What causes the performance to drop so much? So let me get into a little bit of a technical deep dive here. And this slide just talks about, the policers and the WAN links and the higher latency can, not even really high latency, just latency on a WAN at all can really hurt performance. So anytime TCP experiences loss, is in the case of a policer, significant loss, TCP goes through what's called a slow start algorithm. So if you look closely at this diagram, the x-axis is time, and that's in milliseconds, and the y-axis, that's a representation of the number of bytes or sequence number that's sent onto the wire. So TCP is going to ramp up in a staircase manner, and it's going to try to establish the capacity on the network. And it does this by waiting a complete RTT every time it sends basically a packet. Okay, then it'll just continue to ramp up and wait each of those RTTs. So on a WAN link, especially those with large capacity, this slow start period can be very significant. In this example, with even just 10 milliseconds RTT, the slow start penalty is almost 80 milliseconds. So any time TCP gets policed, it's going to go back through this slow start. So this large area that you see, that's basically nothing happening on the wire, and that's happening over and over again. Okay? So what can you do to solve the problem? I guess that's the next logical, question to be asked. So sometimes increasing the CBS value or the buffer size can solve the problem, but in reality, that's not the ideal solution. Increasing a CBS to a really high value allows customer burst to enter the network, but could cause further trouble downstream as other devices would have to be tuned. But to be fair, we've seen cases where for a buffer, a CBS was set too small, as in Rachel's example of a 20 kbyte, and an increase to 64K, 128K, or even larger can solve the problem. But when the end user site is large, and there's a lot of users, the amount of CBS buffering becomes impractical. So as this slide shows, the best practice is to shape the traffic to the contracted CIR rate. So the graph on the left illustrates a gig-E customer LAN traffic without the shaping function, so you can see that it's bursting, right? All of those bursty spikes would get dropped by the policer because the police are set to 100 megabits per second. But the graph on the right shows that if at the egress point of the CPE router, if it's shaped, then the traffic's smooth to 100 megabits per second, and that traffic will not be policed. So that's the ideal situation. And to be clear, shaping can be the responsibility of end customers for business services, but it also could be provider-to-provider interface, such as Ethernet backhaul, because then the provider feeding into the next provider is essentially the customer to the next provider. Okay, so that concludes this section of the webinar. I want to hand this back over to Rachel for wrap-up and then some Q&A.
Thanks, Barry. I also wanted to make one quick point on your last slide that, a question we do get often is, well, why don't we just make all the buffer sizes as large as they can be everywhere in our network so we don't have this problem? And Barry kind of alluded to that, is that doesn't necessarily work for your voice and video traffic because buffers will add delay to the service. So it's really a fine-tuning that needs to happen in terms of buffer sizes in your network. Large enough to handle the bursty data traffic, but not too large that it adds too much delay. So wrapping up kind of, what we've talked about today and demonstrated. This is JDSU's recommended way, and the best way, in our opinion, to test burst. In every Ethernet service verification test that exists, whether it's RFC 2544, Y.1564, RFC 6349, they're looking for kind of two key components. And the first one is looking for network misconfigurations or provisioning problems. So that's kind of one key component. And then the second key component is then looking for ensuring service performance. Now that I know I have X amount of throughput, is it quality throughput? So that is the same approach that we're recommending for testing burst, looking for these two key components. The first one for configuration problems is the CBS test. So the committed burst size test, you're looking or measuring burst size in amount of kilobytes, for example. That's what you're measuring or looking for. And you're looking for a buffer configuration problem. And then the benefit of this, of course, is that you're going to reduce frame loss for your users if the buffer is set large enough for that circuit. So that's part one, looking for configuration problems. Part two is then ensuring that the service performance is of the highest quality that it can be. And that's where the RFC 6349 TrueSpeed comes into play. So this is measuring your higher layer or application throughput. I also like to think of it as measuring customer experience throughput. And it's giving you a measurement in, megabits per second. So the type of problem that this test is looking for is emulating your actual customer experience and the quality of service that they're experiencing. And a key benefit of this is to help eliminate the finger pointing when they complain of a lower throughput than what they're paying for, or also to help find problems through your network. Because what I want to point out to you is that just because a CBS test passes doesn't necessarily mean that the customer or application throughput is going to be good and that will reach 100%. So in the demonstration that we showed you earlier, the network passed a 64 kbyte CBS test with flying colors. There were no issues. But how do you know that a 64 kbyte buffer size or burst capability is actually sufficient enough to provide 100% throughput for your customer applications? There is no direct correlation. So that's why we recommend also doing the TCP throughput test. You could have very poor TCP throughput, like we showed you, around 60 meg instead of the 95 meg TCP throughput it should have been, even with the 64 kbyte burst size passing. So that's why we recommend this two-prong approach to testing burst, looking for both a burst size verification and an application or customer experience throughput verification. And we view this as the best, most complete way to do it. And so for any further information that you want on this topic, you can go to our website, and on jdcu.com we have white papers available for you, videos, app notes, posters. There's a subscription center where you can sign up online to receive updates from us on new software, new capabilities, or collateral for you. And we will also be sending out this recorded webinar to you, to everyone who attended and everyone who registered. That will include a link to a Burst application note that we have available for you. And for our CBS test capabilities in the RFC 2544 and in our Y.1564 tests, that is all available on our T-Bird MTS 8000, 6000A, 5800 portables portfolio, as well as the QT600 with Net Complete, which is our Ethernet probe and software solution. And then the RFC 6349 TrueSpeed, also available in our T-Bird portfolio, the 8000, 6000, and 5800. Okay, so let's take then the last 10 minutes to answer questions.
Thank you, Rachel. I will start reading the questions from the Q&A panel. So the first one is the TrueSpeed test demonstrated here unique to a particular platform, or is it supported across all your platforms? I believe you just answered that question, but if you can please repeat.
Okay, Rachel.
Yeah.
Okay,
yes,
Rachel, take that.
Yes, the TrueSpeed, the RFC 6349, that's available on the T-Bird MTS 8000 with MSAM 6000 and 5800 today.
One more question. Can some or, oh, sorry, it disappeared. Can some or all of the feature tests discussed here today be used for verification of high-speed internet service to a typical residential customer?
Yeah, I mean, if you have the T-Bird products at both locations, there's nothing that prevents you from doing that.
Yep.
Not much more I can add to that. Any other questions, Natalia?
Just going to, there are very few questions in the Q&A panel. Most are actually in the chat panel. There is a question on, can iPerf be used to conduct the TCP test, and what are the limitations of that testing?
Yes, you could do that. The general problem, what we experience very frequently with providers, is that when you're running the iPerf test, it's very dependent on the laptop speed. There's a lot of unknowns as far as customers who don't really know how to set the TCP window, so you get results that are variable and many times inaccurate. But you know, I have seen, you know, some situations where a really knowledgeable person understands some of these limitations and runs it accordingly at the lower rates, that it can be successful. But really what it lacks the most is the automation. You know, if you run this per 6349 and use our TrueSpeed implementation, it's completely automated. And the new version of TrueSpeed that we're going to put out very soon is you just enter the CIR and you really just push go. It computes all the window sizes. It runs an upload and a download test and does everything for you. So I hope that answers that question.
Yeah, and I'll add to that, Barry. So using the iPerf on your laptops, for example, again, you do have that utilization limitation of the bandwidth of your laptops, and it does not. It's a very manual test, so it's not going to automatically test various window sizes or automatically compute for you what the optimal window size should be of that link. It doesn't do an automatic upload then download measurement and follow. It doesn't follow the RFC 6349 test standard either. So there are several limitations to it. It also doesn't provide you pass-fail information. It just gives you a measurement, but you don't know how good or bad that is and what the ideal should be. And that's what TrueSpeed gives you.
Thank you, Rachel. There are more questions about is TrueSpeed or can TrueSpeed be used with the QT600? Are these tests available on the QT600? So several questions with that.
Rachel, I figured I'd let you take that question.
Yeah, not today. It does not support it, and it is on the roadmap for support. I don't have a committed date for you at this time, but if whoever asked that question, if they want to send us an email, we can have one of our PLMs on the QT600 give you more specific roadmap information.
Yeah, there's definitely a lot of questions. I'm looking at them now in the chat panel.
I'm looking at the Q&A panel as well. Let's see. Someone asked, is there a specific software version required to run the TrueSpeed test? So there are software options that are purchasable options for the TCP test capability, and then versions of software. It came out about a year ago, but I recommend that you get the latest version of software, which is available for free on our website. For the 6000, 8000, it would be version 16, and for the 5800, it would be version 3.
Okay. There was a question on, I'm just trying to get through them all. When you perform the CBS burst test during the demo, are these frames packets sent at 1 gig or the CIR rate of 100 meg? Yeah, that's sent at the 1 gig rate. So if it's 64 kbytes, we would burst those up to 1 gig. That's the definition of that test. Do you have any white papers detailing RFC 6349? And yes, as Rachel indicated on the last slide, we have a white paper and an app note and training type videos. Rachel, there was a question. It says in your CBS test example, did the test find that the bottleneck was 20K buffer size, or the test just failed and the vendor told you the buffer size? That was through your case study. You might want to answer that.
Yeah, so the test results show you about how much it was able to burst, and it was, sitting there around the 20 or a little bit less than 20 kbytes, and we had to isolate it to that particular device, in which the default then configuration setting in there was found to be 20 kbytes. But we had an indication of what the bottleneck was based on the test results that indicate around the 20 kbyte size, if you will.
Yeah,
Barry, I see one question. When you performed the CBS test During the demo, are these frames or packets sent at the 1 gig line rate or at the CIR rate of 100 meg?
Oh yeah, I'm sorry, I just answered that one. They're sent at the 1 gig rate.
Okay.
So that one there. Now there was a couple on test options you might want to answer, Rachel, as far as like when the new TrueSpeed will be available and when the CBS will be available. That's very soon, right?
Yes, by the end of this month, actually. So if you have signed up on the subscription center, we'll be able to send you an email notifying you that the new software is available and a link to it. But you can also, check the website. But it should be ready by the end of this month.
There were a couple questions about the HST 3000. Currently, it's not supported, but we are having some internal discussions on whether or not the 3000 could be used, as someone quoted here, as basically a TCP loopback that's been being discussed. I'm just scanning. There's a lot of questions, and we're down to the last minute.
Yes. The CBS test is not a separate option, so that will be included in our RFC 2544 and the YDOT 1564 test for you at no charge. So that is included, a standard feature when it comes out with the new software version for CBS.
And there was a question about CBS test in 1564. Can that be conducted? The answer is yes. In our 1564 implementation, we ran it in 2544 because we know most people run 2544 today, but nothing prevents you from running that in 1564 implementation. And we're down to 1 minute. Trying to think here. Do we want to, Natalia, would you like to wrap up, or is there anything final you would like to say?
If there are no more questions, there are still questions coming with regards to the recorded presentation or the presentation itself. So I can just say that all participants will, within a week, receive an email from JDSU with a recorded link and the presentation with some other resource material as well. So please look for that email. It will come your way shortly. And thank you for joining today.
One more thing, please. Sorry, I noticed there were some very technical questions that it would be difficult to answer. Please contact me directly, barry.constantine@JDSU, if I did not answer the question to your level of detail that you'd like it to be answered. Sorry, Natalia.
Yeah, and I think what we can also do is take a look at all the questions on here that we didn't get a chance to answer and write up some answers, and can include that possibly in the follow-up email that we send all of the attendees with the link to the recording as well.
Okay, great.
So thank you, Rachel, and thank you, Barry, and thank you all participants for joining today's webinar. And this ends today's call. Thank you.
Okay, thanks. Bye-bye.